Alright, now let's talk about the paired t-test in R. The paired t-test can be used when you have two dependent or matched or related samples, like before-after studies or pre-test, post-test studies. For example, let's say you have 100 individuals with high systolic blood pressure, and we give them a specific medication, and then we measure their blood pressure after like 2 weeks. So we want to see whether the mean blood pressure significantly changed or not. Okay, so, or in other words, mean blood pressure before the medication was equals to mean blood pressure after medication or not at the population level. So we use a sample, but our inference is at the population level. The null hypothesis is that the two means of blood pressure are equal, or in other words, the difference of blood pressure was zero, there was no effect. And the alternative hypothesis is that the two means are not equal, or in other words, the difference is not zero, or the treatment had some effect, right? And under null hypothesis, we can calculate the t statistics. So there are several assumptions, like the unpaired t-test. Here we have random samples. The samples that you have must be random. The samples here must be dependent. In the unpaired t-test, the samples must be independent, but here the samples should be dependent, like before, after. And also the difference between the groups should follow approximately normal distribution. So let's see an example to better understand the concept. Here I have two groups. It can be any experiment. So we have the data before the experiment, and we have the data after the experiment for individual, for 1, 2, 3, 4, 5, 6, 7, 8. So for 8 individuals, I have done some experiment. This is before experiment and this is after experiment. Okay, so the values. So you can see that the data are dependent before and after. We have to measure the difference, which is after minus before. Okay. So the null hypothesis in the paired t-test, this is an example of the paired t-test, is that the difference, the mean of the difference, equals to 0, which means that there was no improvement. Okay. After the experiment, there was no improvement at the population level. Okay. And the alternative hypothesis is that the mean is not equals to 0. Sometimes it can be less than, sometimes it can be greater than 0, sometimes it can be not. So it depends on the question, the type of the question. Okay. And the next step is that we have to calculate the t statistics, and then we compare it with the critical value to make decision, right? So how we can calculate the t statistics? So from this column, first of all, I have to measure the mean of the d, which is d bar, which is sum of these values divided by the number of samples gives us the d bar, or the sample mean of difference. And also we have to measure the standard deviation of the difference, right? And once you have everything, once you have d bar and sample standard deviation, we can easily plug them into this formula, that d bar divided by sample standard deviation of difference, and then divided by the square root of n, which is the number of sample size, 1, 2, 3, 4, 5, 6, 7, 8. So your sample size is 8 because it's dependent. And when you calculate the t, you have to compare it with the critical value, and then to make your decision. Let's see an example. Here I have the amount of lactic acid in blood was examined for 10 men before and after a strenuous exercise. And here are the results. So here we have person 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 before the strenuous exercise and after it. And these are the amount of the lactic acid. So we want to test whether the change was significant, right? Or whether the mean before equals the mean after at the population level, or in other words, whether the change was significant or not. And we want to do this at the 99% confidence level. So how we can do this in the R programming language? This one is at 99% confidence level, and also we want to solve it at 95% confidence level. So in R programming language, the first step is that we have to create a command that is a paired t-test, right? Paired t-test of lactic acid. So the first step is to load the data, right? So load the data set, and we use read.csv file.choose and set the header to true. Save it in a object with the name of data2. Okay, so let me run this code. So it asked me where I saved my data, which was in the and lactic acid. So here is the data. We have only 10 observation. Your sample size is very small. That's why the t-test is appropriate. 10 observation and 3 variables. And if you click on this one, you can see the data. We have for 10 individuals, we have the amount of lactic acid before and after of the exercise. So this is the data set that I have. We have to always check the data. Check the data. We can use head of the data set that I have, data2. Here is the data, the first 6 rows. And the next step is to visualize the data, right? It's always a good idea to visualize the data. So we use box plot for before and also after, right? So I'm going to extract from data2 before and also from data2 I'm going to extract after. Okay, so click run. So here is the box plot for the data. So we can make, for example, we can change the color to the first one to red, the second one to blue, and just make this horizontal. LAS equals to 2. Okay, so it seems like the difference, so the amount of lactic acid improved, right? But this is at the sample level. So we're gonna test this at the population level, right? To test whether the results are statistically significant, and they're not by chance, they're not only for this specific sample. Okay, so the null hypothesis is that the mean of the lactic acid before equals the mean of lactic acid after, or in other words, the difference of the mean equals to 0, right? Difference of mean of lactic acid equals to 0, right? And we want to just see that whether they are different or not, right? The alternative hypothesis will be the difference of the mean of lactic acid is not 0, right? So that's the alternative hypothesis. It's a two-sided test. So I'm going to solve this problem in 2 different ways. The first way is just using the formula, and the second way is just using the built-in functions in R. First, solve this problem using the formula. So according to the formula, we have to measure the difference and then standard deviation of it, and then divided by a square root of sample size, right? So let me use the formula. So the method 1 is formula. So first of all, I have to measure the difference, right? So difference after minus before. So I'm gonna use difference as the object. So difference is data 2 after minus data 2 before, right? Before. So that's the difference for each one. But this is for all of each person one by one. But we have to measure the mean of the difference, right? So mean of the diff divided by standard deviation of the, right, SD of diff, and divided by SQRT of n, which was 10 observation, right? 10. And I put denominator in the parentheses, right? So that's the formula. It's a mean of difference divided by standard deviation of difference divided by a square root of n, and then I save it in an object with the name of t1. Okay. So we have the test statistics is 4.93. So what we should do now is we have to compare this with the critical value, right? So here, if I type t-table and I think two-sided or two-tailed. So let me find it. So we're gonna have this test at the 95% confidence. At the 95% confidence interval, right? So at 95% confidence level means that the alpha is 1 minus confidence level, which is 0.05. So the alpha is 0.05, and the degree of freedom in this column is 9, because we have 10 observation. 10 minus 1 is 9, which is 1.823, right? So the interpretation is very easy, that so we can say that the calculated or computed t-test, which is 4.93, was greater than the critical value. So this is at the 95% confidence level, which was 1.3. 1.83, sorry, 1.83. This is 95%. 1.83. 83. So it falls into the rejection area, right? So we can reject the null hypothesis. So we reject the null hypothesis, which means that we reject the difference is equals to 0. So the difference of the mean of lactic acid before and after of the training is not 0, which means that there was improvement from a statistical viewpoint at the population level, right? So, and if I want to test this at the 99% confidence, that one will be, alpha will be 0.01, and the degree of freedom is 9, right? So in this case, alpha will be 0.01, right? And degree of freedom is n minus 1, which is 9. So it's 2.82. Again, it rejects the null hypothesis. So the t-test is greater than 2.82. And again, it rejects the null hypothesis, which means that we are 99% confident that the difference is statistically significant, right? There was a improvement after the strenuous exercise in the amount of the lactic acid in the body of the individuals. Okay, so at the population level. Now I'm going to solve this from the method number 2, which is using the built-in functions in the R. So method 2 is function, or also called p-value technique. So which is super easy. We use, again, it's like the previous test that we used for the unpaired test, t-test. So we used t.test. So the first group, the second group, and let me copy this here. Okay, so that was the first group, which is data after. The second group is data before. So the alternative hypothesis is two-sided, right? Because the direction doesn't really matter, whether it was improvement or not. So we're going to see that whether they are different or not. Okay, so if I want to see whether there was improvement, I use greater. But here we are just interested in to see whether these two groups are different or not. So the alternative is just two-sided. Mu equals to 0, difference is 0, and paired. So the only difference between the paired and unpaired here is that you have to set the paired as true, because this is a paired t-test, right? So you have to just change this to true, variance equal to false, confidence level 2.95, because I want to test it at 95% confidence level. So I select all of these, and when I click run, so you can see that the test statistic, so it's automatically detected that this is the paired t-test because we set the pair to true, and the t-value is equals to the thing that we calculated using the formula, right? 4.93. Degree of freedom is n-1, 9. P-value is very significant, is very close to 0, is less than 0.05 and very close to 0. So the results are significant, right? And also it gives us the confidence interval. So we are 95% confident that they are different, that these two groups are different. Okay, so if I wanted to see whether they are just improvement or not, so here I could use greater, right? If I wanted to test this at confidence level of the 99% confidence level, I want it to be 99% confident that they are different or not. So I changed it to 99%. You can see that it is still significant, right? So there was a significant improvement. So these two groups are significantly different from each other. Finally, notice that we can also compare means of more than two groups, which is the topic of the next video using analysis of variance or ANOVA.